Okay. Well, first of all, I want to say thank you for inviting me. It is a pleasure to be back to CITA. I was talking with Aaron this morning, and I think the last time I was here was probably 2013, so basically when he just joined. So it's been quite a few years. It's great to be back. I've had a great visit so far. I wish I could stick around longer, but I've already been away a lot this fall, and with a newborn, my wife is not super thrilled that I travel too much more, so I'm going to return home tomorrow. Okay, so I'm here to tell you today about enabling multi-messenger astrophysics with LIGO. And I will start with a motivation. I think most of the people in the audience are probably pretty up to date on these sorts of things, so I won't dwell on it. After a bit of motivation, I'll recap the first observation of a binary neutron star merger. This is a unique observation because it not only came to us via gravitational waves, but it also came to us through a host of electromagnetic channels. And I promised the LIGO people in the talk so that they would actually maybe get something new out of this talk, that I would go into a little bit of technical detail on some of the behind the scenes of how we do time domain gravitational wave astronomy, at least from my perspective. And then I'll come back to big picture stuff and mention what I think are maybe a couple of lost opportunities with this event, and how we can try to address those going forward and the challenges of that before I conclude. Okay, so the case for multi-messenger astrophysics, I think, is reasonably clear. Gravitational waves are providing a new sense for the universe. We've already had sight across a huge spectrum of electromagnetic radiation. Gravitational waves offer something that's maybe a little bit more like sound. Unfortunately, not quite as good as smell, but still quite different than what we've been able to observe the universe so far. And of course, the best case scenario is not that we detect something in just either electromagnetic radiation or gravitational radiation, but combined together. And long before the events of this August, neutron star binaries were considered to be really one of the key examples of something that we would expect to be a truly multi-messenger source. So definitely to provide gravitational waves, almost certainly likely to provide electromagnetic radiation across wavelengths, and possibly, if we're lucky, also even detectable neutrinos, though sadly not in this case. And the basic idea is you have two neutron stars that are emitting gravitational waves, losing energy, they smash together, and if the two neutron stars obviously contain matter that's accessible, when the matter smashes together, it's expected to put on a bit of a light show. And I would say a standard scenario before August would have gone something like this. The two neutron stars smash together. That collision sends some matter, some ejecta away at near relativistic speeds, but not quite relativistic speeds. And in addition, the two neutron stars smashing together likely forms a black hole. The black hole is rapidly rotating just from conservation of angular momentum, from the orbital angular momentum, and that can somehow magically drive a jet. And this jet has some relativistic outflow that will eventually that will produce short gamma ray bursts and eventually optical and radio. The key is that people always thought that you would really have to be kind of looking down the barrel of this jet to be able to actually observe any appreciable prompt emission in gamma rays. So if you were off axis as an observer, the expectation was that there really wouldn't be too much necessarily to view promptly. But this ejecta that went off at the time of the collision would likely produce, through various nuclear reactions, likely produce a signal that could be visible in the optical on sort of day timescales, and other wavelengths as well, but roughly speaking optical. And eventually, at much later times, radio. So this was sort of what we had expected. Now, before August, I think it's fair to say that because people thought that this opening angle in the jet was relatively small, that the chance coincidence with the gamma ray burst was reasonably low, and that it may be more likely to actually identify this other electromagnetic counterpart, which was emitted more isotropically, called a kilonova. And we'll see how that played out in a second. Because of this and many other reasons for possible joint observations of electromagnetic and gravitational waves, LIGO has really been going after multi-messenger observations for more than a decade. I mean, these ideas started long before even that. But since even the initial LIGO the initial LIGO observing runs, we had formed partnerships with various astronomical facilities. So ground-based transient telescopes, radio, space-based telescopes. I've always enjoyed this picture of Swift. It looks like the Swift death ray. It's not actually firing gamma rays at something, but anyway, time reversal symmetry. I don't know. Anyway, so there's the Swift space detectors and others, and of course LIGO playing the role of the gravitational wave detectors, and I should say IceCube as well. I come from a background that was interested in this for a long time. So my group at Penn State is one of the groups that's developing LIGO real-time searches. And essentially, it's step 1 or 2, depending on how you want to start counting. Basically, once the gravitational wave data is collected at the observatories, the next step is to do a deep search for gravitational wave signals and then use that to alert all of the astronomer partnerships that we have, at this point now 70 in total, who are, of course have been eager to follow up gravitational wave events. We work with a bunch of people. Some of the big collaborations come from University of Tokyo, University of Wisconsin-Milwaukee, Caltech, Kenyon College, and other places. But I really wanted to point out this slide. I normally don't even call this out, except I really want to point out that a lot of the work that was ultimately done was done here at CITA by your very own Kip Cannon. And so I used to collaborate. I still collaborate with Kip quite a bit. I used to make the trek over to CITA pretty regularly when I was a postdoc at Perimeter. So keep that in mind when you're seeing some of the work that I'm describing. OK, so on August 17th, 2017, at about 8:30 a.m. on the East Coast, Advanced LIGO detected the first ever binary neutron star merger. And this in and of itself was a kind of crazy thing, and it just got crazier as the day went on. So we knew quite a bit just within even the first 7 minutes of this detection. So within 7 minutes of the signal arriving at Earth, we already knew that this event was extremely significant. If we want to characterize how long we would have to take for the instrument noise to produce something like this, we had an estimate at that time, which was 1 per 10,000 years. The true estimate's way, way better than even this. We knew that this event was likely to be a BNS. The real-time analysis provides a point estimate for the masses, and it was 1.24 and 1.53 solar masses, which the total mass agrees quite well, I think, with the final estimated total mass. We also knew that it was extremely close, so a distance of somewhere between 40 and 50 megaparsecs, and we had an extremely coarse sky position. So we knew all of this essentially instantly, and over the course of the next 20, 25 minutes, managed to come up with the first GCN notice that was sent out. And here you can see the Hanford LIGO data. This is frequency on the y-axis, time on the x-axis, centered at the time of the estimated coalescence time when the two neutron stars merged together. And you can see it's kind of faint, but you can see this line here that follows a typical chirp frequency, a chirp pattern, which is increasing in frequency, and it's a little bit difficult to tell, but also somewhat in amplitude.
Can I ask you a quick question?
Of course.
So this is software, is like fast-load software. How automated is it? So when you say it got those results in a very short time, did it require a lot of human intervention, or is this pipeline set up that it takes an anomaly and does some preliminary analysis and then stuff comes?
Yeah, so it's entirely automated, though there is a lot of human intervention that happens at the end, which I will talk about as.
But mass estimates
yeah.
Came out as just,
yeah.
Here's something, this is what it would be. That's right.
That's right, yeah, that's right. And so I'll talk a little bit more about exactly how we do this. And of course, I mean, these are all preliminary things that come out in real time, but in this case, it actually ended up being pretty close to what the final answer was. Okay, so this in and of itself was already reason to celebrate. Those of us in the field had been looking for this kind of an event forever. I mean, as long as I've been doing physics, I knew this was my goal. So already pretty cool, but even cooler was that 1.7 seconds later, the Fermi gamma ray telescope and the Integral mission also detected a short gamma ray burst immediately after the coalescence. So here you can again see one of these time frequency plots at time t equals 0. This is when the two stars smash together. You can see the gravitational wave chirping upwards. This indicates the coalescence time, and shortly after was registered a short, hard gamma ray burst. This is another thing that's fully automated. So we get this alert from Fermi. It shows up in our database. And again, within literally, as soon as we were able to look at the data, we essentially knew that there was a holy grail of multi-messenger astrophysics had just occurred. The real-time analysis that does this association with GRBs has a preset set of thresholds that tries to associate these two things in coincidence and calculate the probability that it would happen randomly. And the rate at which we would expect a coincidence like this to happen just completely randomly was already estimated to be much less than 1 per million years. So this is all stuff that we knew in the first 7 minutes. Now, as cool as that all was, there were problems. I was personally still happy anyway. These problems seemed minor at this point, but they were actually pretty important for how the event unfolded going forward. First, we only observed this initially in one of the LIGO detectors, so just in the Hanford detector in Washington. And this is problematic because it clearly didn't prevent us from finding it, but it meant that this was our initial sky localization. So the red here, deep red, indicates the probability map on the sky. And well, I don't know what the square degrees of this is, but like half of the sky, something like that. A tremendously large fraction of the sky. We essentially knew kind of where it wasn't, but that was about it. So unfortunately, we had very poor position information. We did get some confirmation, though, that the likely distance was extremely close, and this was important. I should say, though, that the first GCNs, we did include the Fermi sky location. Unfortunately, we only detected with GBM, or the Fermi only detected with GBM, so the sky position was quite poor. This actually isn't even the initial map, so this is a bit of a lie already. The initial map was a little bit broader. But this is 11 or 1,200 square degrees. It's a very large sky localization here shown in the pink. This green, we'll find out later on, was the ultimate sky localization provided by LIGO eventually. So this is essentially all we knew at the instant that the detection occurred in terms of possible positions. So why was it that we only found it in Hanford? Well, there were two completely independent things that had gone wrong at that instant. One, data from our partner in Italy, the Virgo gravitational wave detector in Italy, had actually stopped being transferred something like 20 or 25 minutes before. So it comes across the Atlantic. Whatever process was managing that getting across the Atlantic had died. So we did not have Virgo data. This was kind of a double whammy. So not only did we not have Virgo data, but the automated analysis actually expects this data to be there, and so it waits for it. And it has a timeout. It doesn't require human intervention, but it was at least a 5-minute delay until that timeout had passed before we even started processing the data. Had this not happened, we would have actually had this neutron star detection within probably 30 seconds. So, I mean, not that it would have made necessarily a huge deal, but this did end up actually delaying the processing. And the second thing that happened that was quite independent was there was a huge glitch in Livingston. And glitch is our colloquialism for large non-stationary noise. So if you look at the time frequency map, again, frequency time from the LIGO Livingston detector, the raw data shows this nice chirp, but then unfortunately has this giant spike. And this giant spike is problematic no matter what, but it was especially problematic because it happened to occur so close to the coalescence time of the neutron star merger. So this is what prevented us from actually identifying the signal automatically in Livingston. And even when we were able to go back and look at the data, we knew that this was likely to be corrupting the result to some extent and had to be dealt with before we could come up with a sky map. It was dealt with in various ways. Online, a team went to work to try to basically just excise it with some smooth window, but it was also possible to fit it and actually subtract it from the data. If you actually look at the data after it's been fitted and subtracted, it's beautifully clean data. So here's the LIGO Livingston time frequency map now with the glitch removed. But unfortunately, this was not the situation that we had in real time. OK, so the next 10 hours.
Can I ask you a question about that?
Yeah, of course.
Having seen this often, I'm struck by how good the LIGO Livingston is. Is some of that a result of the effect of cleaning to get rid of that, so that if more cleaning had been done on LIGO Hanford, it would have been a strong clean signal? That is to say, is this image enhancement or is it raw?
No, the LIGO Livingston SNR was just higher. So Livingston was a more sensitive detector.
Right. So these images are a fair representation of the relative strengths.
I believe so. I'm hoping that whoever made these figures used the same scale. We normally do. So it really should be representative of the relative strength. Yeah.
But so on the normalization, I'm pretty sure that there might not be the same normalization in all the time frequency plots that you show.
Probably not in all the time. Yes, that's true. So across figures, I make no claims. The first one that I showed was like the automated one. It was just whatever it comes out. So that's definitely true. But I hope that these two are the same. I think they are. My understanding was that they are. Everyone's like,
They're in the same figure.
well.
That's why I'm asking.
No, so certainly my expectation is that this is consistent with the fact that Livingston was just way more sensitive. Well, relatively more sensitive.
But at the same time, the fact that you don't see the track in this normalization in Hanford doesn't mean that we don't get loads and loads of information from where the track should be.
That's right. Yeah, I mean, even.
In the sense that, like, we don't actually use these plots for anything apart from showing stuff.
That's a great point, and thank you for reminding me to tell everyone that. So in actual fact, as Carl points out, I mean, these plots are mostly eye candy in the sense that this is not how we actually look for gravitational waves. So there's a coherent integration of the waveform against the data that pulls it out. And I'll get to that actually later.
I'm actually surprised that the coverage wouldn't show those sorts of things here. I mean, it's like being filtered.
Yeah, I mean, we do. So we've shown signal-to-noise ratio time series in various papers. I guess not in this one, huh? I don't think it's showed up in any of them. Maybe a future version will.
Sometimes we show the waveform, which is like the meter. Like that is the signal we think we recovered. We show that error bars. Not in this paper because the signal goes on for ever and ever.
But I mean, we have shown like the raw filter output. So like the signal-to-noise ratio time series, you can see it peak. It's been in I think almost all the papers except for. Actually, it wasn't in the original paper either. The first detection. Okay, so the next 10 hours, this is sort of what happened. So it took about 4 hours for a lot of folks working very hard in the collaboration to clean this L1 data and of course transfer the missing Virgo data. At that point, people were able to do a reanalysis and get a sky map about 4 hours after the initial detection. And during this time, a deeper Bayesian analysis of the binary parameters was being done, and the first one completed in 10 hours. They gave pretty consistent results. The sky maps were offset a little wee bit, but they were both right around 30 square degrees. So you can see the sky maps here that were ultimately generated. At this point, after all the data cleaning had been done and we looked at everything, we knew that the network SNR, this is the sum of the squares of the SNRs from all of the detectors, was about 32. And the signal was easily 100 seconds in band. Depending on how you want to start counting it, it could have even been longer. We actually integrate from 15 hertz in the online analysis, and so that meant that it was actually 6 minutes in our filter integral. Okay, so this all took a lot longer, so it's not really in the same time order, but continued processing of this data, trying to estimate the binary parameters, basically showed, at least so far, this is consistent with a 1.36 solar mass binary, but of course it's probably a mass ratio. The mass ratio is decently well constrained if you assume the component objects have relatively small spin. So I think the constraint is like a mass ratio of 0.8 or something at the 90% level, if I remember right, assuming that the components have small spins. The initial paper indicates that what the object is compact. We have some constraints on tidal deformations, but haven't measured a definitive tidal deformation away from 0. And we're not sure if the remnant is a black hole or a hypermassive neutron star, though I think the electromagnetic community is maybe settling on this possibility at this point. We knew also that the final distance ended up being 40 megaparsecs, and there's an extra bit of that I'll talk about here in a second. Here is just one plot, and I'm sure you've seen these sorts of things a lot from Carl and Katerina and Aaron, showing the two-dimensional probability distribution and component masses, so M2 and M1. And you can see this two-dimensional PDF is really kind of tracing out a single one-dimensional parameter here, which is the chirp mass, which predominantly determines the phasing of the binary waveform. But when you project it down onto the x and y axes, the M1 and M2, things are a bit broader. Here is the two different prior assumptions on the z components of the spin. So in this case, it's essentially a very small spin, and in this case, the spin is approaching the biggest value it could take on for a black hole. It's worth pointing out that at least with this initial measurement, given that we don't have a definitive tidal deformation in this, in principle, we couldn't tell that these things weren't black holes. And of course, we think that probably at least one of them wasn't, for good reasons. And the good reasons I'll get to here in a second. I love this figure. This is just a cool figure, or a cool movie made by Ben Farr. It just gives you a sense of how different this was compared to everything else LIGO has detected. So all these little dinky waveforms here are the black holes that at this time had been published. And the longest one lasted in band only 2 seconds. But this neutron star merger just keeps going and going and going and going. And I always joke that I've never actually seen the end of this movie, and I am not going to change that today. You can feel free to look it up yourselves. Trust me, it just keeps going and going. So the second messenger, electromagnetic radiation, really came with quite an entourage. It wasn't just the gamma rays, which was, of course, already super cool. But about 10 hours later, after people were able to actually get seeing in Chile, there was a detection by the SWOP team with a new transient source located just outside of galaxy NGC 4993, or just at the edge, rather. And you can basically see the comparison image from a previous image of that galaxy showing no transient at this point. After this initial discovery, and by the way, I should say that many teams essentially independently imaged this. Things were happening very quickly. As soon as people were able to actually look at the sky, several teams independently imaged this. This was just the first team that actually had gotten the GCN out. This enabled a lot of additional deeper observations. Once we have this really well-refined sky position, it was then possible, for example, to do deep follow-up with infrared and UV. Swift pointed its UV telescope right at the source. And so we essentially had UV and infrared almost immediately after the optical counterpart. It took 9 days before there was any observed X-ray, and then 16 days later, radio. So if you look at this nice timeline of observations from the electromagnetic side, well, actually, and also gravitational waves, of course. Gravitational waves started all off. Everything else here is electromagnetic observations in different wavelengths with different instruments. So t equals 0 is the coalescence time. We, in principle, started observing this neutron star binary before it coalesced, of course. The gamma rays came shortly after coalescence. And then eventually optical, infrared, UV, X-ray, and radio. As I sort of already hinted, sadly, this detection did not come with any neutrinos. There was a search for coincident neutrinos that didn't recover anything. I'm not an expert in modeling neutrino emission from these sorts of systems, but my understanding from talking with people is that this thing was actually close enough that it was getting kind of interesting. Certainly we expect neutrinos coming out of these sorts of systems, but maybe they can only be detected to, say, 20 megaparsecs in certain cases. So depending on who you ask and who your favorite model is, it was getting close, but still I would say not necessarily in a place where we would expect neutrinos yet. But better luck next time. Yeah?
What are these little
vertical lines?
This is,
No, on the.
oh, thank you. I was going to say that. That's a great question. I totally meant to say it. So the big circles represent the observations. The vertical lines represent times when GCNs were sent by the different teams. So it kind of gives you a sense of sort of human element here. Obviously, given that it's a logarithmic scale, you kind of get this compression in terms of frequency of these little bars. But it was a very active couple of weeks, sending GCNs among the internal partners and LIGO.
What about the 6 that are the GW?
Well, we sent the first one saying, oh my god, oh my god, oh my god. And then we sent the second one, which is a slightly updated version of that, but still without too much merit. I forget which one we said it was a likely binary neutron star. It might have actually been the second one.
So this is as the localization is improving?
This is even before we had localization. It wasn't until this one, or...
Yeah, I think the third one.
I think it was the third.
The third, or was it the fourth? All right. So I was actually going to say that it was this one.
The third has base star, the fourth has low inference.
No, but there's this one too. I think this was all inference. Yes.
We don't know.
Information was coming out. I mean, the first half an hour or so was pretty wild. In fact, my students tell me I was non-functional at the time. I don't actually remember it. It was a bit of a blur. But I wasn't able to type or talk or walk or anything. So, so I don't know. I remember the event and then that was it. I had enough energy to, I'll tell you here in a second how it unfolded, but I had enough energy to type a couple of important commands into a computer, but that was pretty much it. And then I was out. All right, so I have not made any attempt to summarize the vast amount of knowledge from this. I wanted to pick just one that I think was kind of fun because, I don't know, if you would have asked me if we'd have been doing this anytime soon, I would have said no. So given that we ultimately were able to identify the host galaxy of this event and that it was so close and many, many other things, the LIGO collaboration and the EM partners took a stab at actually trying to measure the Hubble constant. So in the local universe, the rate of expansion, or the velocity associated with the expansion of the universe is proportional to the distance through the Hubble constant. And gravitational waves give us a good estimate of the luminosity distance. Essentially, if you know the other parameters of the binary, masses, spins, position in the sky, et cetera, then just from the gravitational wave amplitude, you can work out what the distance is. So since we had a host galaxy where there was an attempt made to try to basically figure out what the Hubble velocity was, admittedly, it's a little challenging because since it was so close, there's a lot of peculiar velocity to worry about. But people took a stab at it, came up with an estimate for the Hubble velocity, and then also had, of course, an estimate of the distance. And when you do that, in terms of the probability distribution for h naught from the gravitational waves, you get this blue distribution here. And so this is the standard units, kilometers per second per megaparsec. And the peak is around 70. For reference, two competing measures of the Hubble constant, one from Planck and one from supernovas, are shown here. And of course, the LIGO estimate is nowhere near competitive in terms of the width, but it's interesting that it's at least consistent, which is good. Otherwise, things would have been strange. And provides an entirely independent estimate of this. It's really something truly unique. OK, but aside from that, probably the more interesting thing we can go back and examine is is whether or not our expectations in terms of the BNS plus GRB picture ended up being what we had expected them to be. And if instead of trying to solve for the Hubble constant, we do a reasonable thing and assume that one of them is already right, then one of the things we're able to constrain is the viewing angle of this, which is like the inclination angle, but it doesn't matter if it's face on or face off. So that's what it's called, the viewing angle. And depending on which Hubble constant you pick, it's constrained to be something less than about 30 degrees. You can look at these plots here. So we can go back and think about this picture, and we know that this viewing angle was less than 30 degrees from the gravitational wave measurements, but there's a good reason to believe that it's also greater than 0. So the GRB that was associated with this event was extremely weak, and also 10 times closer than anything else in its class. So other short GRBs were at ranges of 400 megaparsecs, the closest one, I think, about 400 megaparsecs. And so this GRB was extremely close and significantly weaker. And so these things together kind of indicate that we probably were observing this off-axis, so at an angle that's larger than the jet angle. And sort of the simplest models for this wouldn't have expected this to happen at all. But now it's kind of an open question. How common is this? Should we be rethinking a lot of the prompt emission mechanisms? And I think that's currently what people are thinking about carefully. OK, so I'm actually going to take a minute now to go into a little bit of some of the behind the scenes, some of the technical stuff. And then I'll come back to big picture here in a second. So how do we do time domain gravitational wave astronomy? So our basic multi-messenger workflow tends to look something like this. We take data from all of the gravitational wave observatories that we have. In this case, it's the 2 LIGO observatories, H1, L1, and the Virgo observatory, V1. It goes into some real-time analysis engine. And we have several of these. They're targeting, in some cases, different sources, in some cases, the same sources. But they're all programmed to do what they do in a completely automated way. And their goal is to figure out if there's something interesting in the data. And if an interesting candidate is discovered, then it is uploaded to our gravitational wave candidate event database. Here I've shown a screenshot of that. And so we essentially know quite a bit of stuff right when it happens. So this is the numerical data that gets put in here. Basically, the point is we know things about point estimates for the mass, the signal-to-noise ratio, the false alarm probability, et cetera, et cetera. And what's even more important than just this initial upload is that it really serves as a point of automating several other analyses. So namely, a deeper parameter estimation of the, a deeper estimation of the binary parameters plus other follow-up. And it also serves as the point which generates alerts to our internal community, which at this point have to go through a human vetting. So under normal circumstances, if GraceDB gets an alert, gets an event that's interesting that passes some sort of threshold, in this case once per month false alarm rate, then humans are notified via a telephone call, basically, in an automated way. For this particular event, this part didn't happen in the normal way. So because this event was found only in the single LIGO detector, the automated alerts to LIGO didn't work. Several of us who work on real-time analyses had our own text messages set up basically to be able to sort of do this, get these alerts with our own thresholds applied. And so fortunately, several people had actually gotten this alert. And then we were able to essentially go in by hand and alert the rest of the community. That was the one thing I was able to do while I was still functioning. I pressed a couple of buttons, and then people were alerted. So this human vetting process for a candidate is at this point required, although I hope to get rid of this soon, before we alert our astronomy partners. And then one other thing I want to say is that then, once this happens, there's now sort of feedback between the broader community. So this stop sign here, you can imagine being all of our astronomy partners, being able to get information from GraceDB and also return information to GraceDB. So here you can see, images of certain surveys, how they've tiled the sky. This is a neutrino candidates. None of them ended up panning out. But essentially, we have in real time a full log of all the interesting things that are going on with a given gravitational wave candidate. Now, defining interesting in the case of compact binary mergers involves matched filtering, and specifically the type of analysis that I'll be talking about actually is doing this purely in the time domain. And the basic idea is if we've got some gravitational wave data here in this black data set here, we're going to convolve a given gravitational wave template, a model of what the waveform should look like across the data. It's like a sliding dot product. And out comes a time series. If this is normalized properly, this time series really has meaning in terms of a signal-to-noise ratio. So you can see, if you just look at this black data here, this black stream of data, it's, I don't know, by my eye, I wouldn't see anything interesting. But at time t equals 8 seconds, there's this nice sharp peak in SNR. The biggest problem with compact binary searches is that we don't know in advance exactly what we're going to get, in the sense that we can model any particular binary decently well, but we don't know what's out there in nature. So it's not like we have a bunch of photographs of these things saying, oh, there's going to be a 3 solar mass and 10 solar mass black hole merging in 10 minutes. Let's look for that. We're doing a completely blind search. And so we have to pick a plausible parameter space and look for all of these models in parallel. So in reality, we're sort of streaming LIGO data against a whole collection of models. Here I've shown just 3. In actual fact, there are a lot. We do this in the time domain because in principle, it has theoretically 0 latency. So we really want to get ready for a case where there really is a fully robotic, no humans involved follow-up of these sorts of candidates. And I'll talk about this here in a second. Our actual implementation of this gets answers out in about 15 seconds. So we have a little ways to go, but are making good progress. The gravitational wave templates that we pick span what we consider to be a reasonably plausible binary parameter space. So we start at 1 solar mass in component mass and go up to a few hundred solar masses. So here you can see a plot of component masses M1 and M2. Each one of these little dots, which is almost entirely invisible to you, I'm sure, represents a different, unique binary model that we searched for in real time in parallel for this search. And the basic idea is that we pack these densely enough so that if the real signal lies somewhere where there isn't a dot, then we detect it with reasonably high fidelity. We search for intrinsic binary parameters. So we, of course, have the 2 component masses. We also consider 2 degrees of freedom for the spin. So each black hole or neutron star could spin. So it could orbit around, it could be rotating about its own axis. And those spins, of course, are vector quantities. So there are 3 components that define the direction of the spin relative to the orbital angular momentum. We only allow in the search pipelines to model spins that are aligned with the orbital angular momentum. So they're either parallel or anti-parallel or one of each. But we don't allow any components of the spin to be in the orbital plane. And furthermore, we only allow the spins to be large on the black hole and actually restrict the spins to be relatively small on the neutron star masses. So any template waveform that has a mass below 2 solar masses, we restrict the spins. So a way of visualizing that is versus chert mass, which is a special combination of masses here, and this parameter chi, which is the chi effective, which is the spin, which is the mass-weighted combination of the 2 component spins. And you can kind of see that it does this funny tapering. And in general, the range of chi is very small at low mass. This is the neutron star region. And then this tapering is caused by neutron star black hole systems. So my main reason for showing this is that essentially anything that you might call interesting is defined by this initial parameter space. What your wonderful LIGO folks here do is way cooler and way better than any of this. They can do a much deeper, more thorough search of the data, considering physics that we don't even begin to try to address at this level. But unfortunately, unless someone tells them where to look at the moment, they're not going to get it. So if you want to say what is wrong with LIGO, then you can say me and the people who work on this sort of stuff, because we're really dropping the ball in some sense by introducing some pretty early selection effects potentially. Now, we don't have any reason necessarily to believe that we're missing some large class of things, but I'm just telling you there's only so much that we're currently doing at this stage. And if it doesn't get past this, then it doesn't happen. One other quick thing, and like I said, this is really mostly for the benefit of the LIGO folks here, because I don't think they've ever heard me specifically talk about this. Our time domain match filtering, if you did it naively by convolving all these waveforms, would be literally impossible. It would require like all the computers in the world. Clearly, we're not going to do that. We actually accomplished this by finding an orthogonal decomposition of the binary parameter space. And this makes it possible. So if you imagine this convolution of all of these model waveforms, h sub alpha, where alpha denotes this individual discrete point in the bank. So there's 600,000 of these, with a data stream with a time index I then we compute an SNR time series rho as a function of the template alpha for each sample point in time I. We basically rewrite this as the linear combination of a different set of inner products with something that is not a binary neutron, or not a binary waveform, but something different, and then form linear combinations to this matrix. Pictorially, this is what's going on. We want to accomplish this. Mathematically, this is very expensive, so instead we do this. These things look nothing like binary waveforms, but when you add the outputs of these things together, miraculously, you get the thing you were looking for. The big advantage to doing this is that we have fewer inner products. So K has fewer elements than alpha, and each one of these inner products we're able to optimize to make very inexpensive computationally. And that all combined together makes this possible. And I think there's potential for a lot more here. And it's going to require some work, but we did some initial work that seemed to indicate that this is interesting. If we go back to just the two component masses that we're looking for in our search templates, and we sort of ignore the other parameters for a second, just focus on two parameters, so mass 1, mass 2, we're laying down some grid of possible binary parameters. And we know that this orthogonal decomposition works just fine if we're trying to look for a signal that exactly matches one of the initial grid points in our template bank. But a natural question to ask is this decomposition complete? Have we actually extracted in some reasonably well-defined way all of the information from the data to be able to figure out signals which have parameters that lie in between our original set? And as far as we can tell, the answer to that question is yes. Essentially, the idea is to take this initial reconstruction matrix, rather than having some discrete set of parameters that you're trying to calculate it for alpha, to actually have a function that takes as a continuous distribution the input parameters for the binary, and essentially to interpolate any possible binary waveform in this parameter space. And you get a sense of why this might work by looking at some of these matrix elements, M sub k, for the continuous total mass in Q space. Here's the third basis vector. Here's the 21st basis vector. And these functions are relatively smooth. And so the idea is that you can sort of interpolate anywhere in here and actually figure out the signal-to-noise ratio for any binary, even if it doesn't fall on the initial parameter space point. We believe that we are that we really are extracting all the information from the data in some limited parameter space, because we've checked when we build this orthogonal basis, the natural question is, does it change when you keep on adding more waveforms? And the answer is no. Once we get a density here where the spacing between these things reach some critical distance, then essentially the orthonormal basis stops evolving, and it looks like we've really extracted something that's relatively complete. So we may be able to do something more clever than what we're currently doing, which is just reconstructing these individual points. And perhaps if we're really, really clever, there may be ways of actually expanding the parameter space in an efficient way and getting rid of some of these selection effects. All right, I promise to go back to big picture now. That was for coffee conversation to get the juices flowing and the LIGO crowd here.
So has machine learning been used?
It's really funny you brought that up, because I've been talking a lot about machine learning lately. People are starting to look at it pretty seriously from a detection standpoint. I'll talk in here in a second about something we're doing from a data quality perspective, where it has a lot of potential there, because there are fewer things that are modeled, and it's sort of nice to be able to throw your hands up and let the machines figure it out. There are some claims that have been made that, in my opinion, are probably false regarding detecting gravitational waves with machine learning. However, I do know that there are some people who are working on it that I consider to be pretty good. And if what they're doing pans out, then I think there's promise. I don't know how relevant it'll be for LIGO, but if I were a student thinking about LISA, for example, the space-based mission that's going to fly in 20 years, I would be seriously considering machine learning as a possible way for data analysis for that mission. Because I think it's so far away that if you just sort of figure out how things are evolving in terms of the machine learning community, it may be inevitable that that's just the way you should do data analysis in 2035. I don't know, but I would take it pretty seriously. Okay, so back to some big picture stuff. One of the big lost opportunities, I think, for this event was, although we had all these great observations, in this pink region, this is essentially time where we did not have observations in these wavelengths. Okay, so it wasn't until the first optical observation that we could pinpoint the sky location enough to be able to do all of these other observations. So when we don't have observations here, it's not saying that there wasn't actual emission in these wavelengths before this. It's just that we don't know, right? And given that we now maybe have to rethink some of the prompt emission mechanisms, in my opinion, we can talk about models until we're all blue in the face, and we should talk about models. But if we can get some early data in these other wavelengths, it might really help to try to sort of figure out what's going on at the promptest emission of electromagnetic radiation. Okay, so to do this, to really get to this pink region, we want lower latency gravitational wave alerts. This should be possible. So what limits us now, it takes about 10 seconds to calibrate the data. It takes 4 seconds to transfer the data from the observatories to a central location for computing. It only takes 5 seconds to search all the models. That's the kind of silly part of this. The hardest part has been made very fast. It takes about 5 seconds for sky localization. And then the elephant in the room is the, at best, 30-minute human vetting time, which is all fun and all, but needs to die. And there's a plan for this to die in the next science run. I don't know when, but hopefully very shortly after we first start observing again, once we're sure everything is reasonably stable. So in this case, we're already down to like realistically being able to send out alerts in maybe 30 seconds. We can do that today. You take this out and we're good. In reality, I think people are going to push these things down even more. We should be able to get down to a few seconds end to end. So we really do have a shot at being able to provide latencies that are extremely low. And I think the motivation for doing this is that there will be extremely powerful robotic surveys in the future. There already are, but this is just how things are going. So LSST is an example. They don't have a lot of target of opportunity time, but they seem to have some. And they seem to maybe be interested in LIGO, and perhaps even more interested in LIGO now. So this is kind of a crazy instrument. It'll take a 10 square degree field of view, extremely deep. It can slew relatively quickly. And if this big beast can actually be pointing crazy places in the sky and imaging really deep, really quickly, we certainly don't want the gravitational wave detections to be the limiting case. And so we really need to be thinking about not only LSST, but other missions that are going to have like really impressive capabilities in terms of transient astronomy. And one of the more crazy ideas, which is becoming less and less crazy, it was crazy, a decade ago when we first started working on it seriously. Now it's becoming much less crazy, is the idea that it's actually possible to alert astronomers even before the merger happens. So if you look at the length of a binary neutron star waveform, when we're at design sensitivity for LIGO, it might last 1,000 seconds. If you integrate this waveform up to the minute before merger, then you'll already have accumulated enough signal-to-noise ratio to determine that there's gravitational wave. That leaves open this band of a minute before the actual merger to actually alert people and to, in principle, be slewing instruments to detect this prompt emission. And I said this would be crazy before, but I don't know, now neutron stars, they exist, they're loud, they're nearby, LIGO's working, who knows? From the perspective of just being able to make the detections, it's actually very compelling. So if you consider the advanced LIGO number of detections per year normalized to design sensitivity, essentially we should be able to detect 10 neutron star mergers per year, 10 seconds before coalescence. The problem is the sky localization is bad. If you look at what the localization is for those same sources, it's going to be about 1,000 square degrees, which is kind of lousy. This is possible, though, that with X-ray emissions and other things in space, that this is still quite relevant if those things pan out. But even with LSST, a single pointing, it's possible that maybe of order 1 time per year, you could send an alert out a few seconds before coalescence, have LSST on the target and image essentially right when prompt emissions should start. It's a bit of a long shot, but it is not, literally, it's not impossible. It'll be a little bit of luck, but it is like a 10, 20% kind of thing that could happen. So I think it's worth pursuing, even as crazy as it sounds.
So what's the limiting factor on the sky localization here? Is it really just that the SNR is always going to be at threshold when we decide we'll send this early alert?
No, that's an excellent question. And I'm glad you brought it up because it gives me an opportunity to expand a little bit on this. This is assuming diffraction limited. So the issue is lambda over d. And the problem is that this early bit is low frequency. So very long gravitational wavelength. And that's essentially what spoils the sky localization.
Okay, so it really is a fundamental barrier.
Sort of. So there is another term in this that we don't take into account when we do this calculation. That since talking with Latham Boyle at PI, I've remembered a little bit about this, and he convinced me of. And bottom line, we should make this with a better calculation. Like, for example, Lau inference. You might find that Lau inference actually does substantially better than this, and there's a good reason to believe that. Because at some point, there's a term that is better than diffraction limited, and we can talk about it later.
Low inference station takes 3 days to run.
Well, but it's a proof of principle, right? I mean, you can always make stuff faster. The question is it physically impossible? I'm not worried about the speed. The question is there a physics reason why it's literally impossible? And I think that this is too pessimistic, in my opinion. Not by a lot. I mean, maybe a factor of 2 or something. But I wouldn't be surprised if the real answer is a little bit more optimistic than this. And we could test that with Lau inference. OK. Noise mitigation, I'll go quickly through this. Clearly, we understand that there are issues here that need to be addressed from this event. I mean, this had a huge impact on this. It really did change how this event was dealt with. But it also leads to other issues. All these glitches are present in the data all the time. They make the search less sensitive, and they increase the risk of sending false triggers to important surveys. LSST doesn't want to be pointing at garbage. I think each pointing is like $1 billion. So that's the technical amount of money. So clearly, we need to have this all well under control in the area of fully automated alerts. And the way I think, so certainly some people in my group are approaching this. We normally think of LIGO as just a strain detector, but in reality, there's a tremendous amount of information gathered along with the strain. There are accelerometers, microphones, magnetometers, seismometers, radio antennas, all kinds of things that are monitoring the state of the instrument, not including all of the additional control signals and things that are being recorded. And here's a case where people have already made progress using machine learning techniques to sort of sort all of this data out, and we're trying to push it even harder to have in place for O3, to have a real-time assessment of data quality so we can be doing some form of cleaning online. Not as sophisticated as what people ultimately do, but hopefully we can start to address it a little bit better. So in conclusion, I think the next frontier for this will be to push to observe the promptest emission across all the wavelengths and to figure out precisely what's going on at merger time to see if we can understand the prompt emission physics. And to do this, we'll have to alert instruments as promptly as possible. We want to get the gravitational wave alert out as quickly as possible and hope that some instrument can find it quickly, pinpoint its position, and then enable a deeper follow-up. And that's all. Thank you.
Are there any questions for chat?
I thought for the optical, part of the issue was they just had to wait for it to become nighttime.
Yeah.
So is there a problem that there aren't enough observatories like on the eastern part of the world or the south, for example?
That's almost certainly the case. Though I don't know. I'm not qualified to say that in general, like if there are enough. I mean, clearly we have a select number of observatories that are operating with us. One of the things that I'll say that's kind of crazy about this event, right, is that people had assumed implicitly that only the most sophisticated telescopes, bigger than a meter scale, were going to even have any shot at detecting these signals. And that's just false. Like practically any amateur with a I don't know what the limiting magnitude is, but maybe a 12-inch telescope with good seeing would have found this thing.
This one.
Yeah, this one. But I mean this one. I mean, like, yeah, it'll happen again, right? And so I think there's reason to be not quite as pessimistic going forward So I don't know that we really, I don't personally have a good answer to, do we have enough telescopes in general? For this event, I feel like had we had more telescopes, things could have been different. But whether or not that would be true going forward, I don't know.
I think that maybe if the data hadn't been misbehaving as much as it was, like if we had been able to do the 20-30 minutes nominal delay time that we are able to do when data isn't misbehaving, there might have been a slim chance that the South African telescopes could have received something. But I think that was, well, yeah. There would have been, like, I think we would have had to been lucky in the timing for that to happen.
Had BAT seen it as well? I mean, this, even from the gamma ray perspective, this was a poorly localized source. If it had gone differently in gamma ray, then it would have been a very different story. We could have had localization much earlier. And I mean, even though it would have been delayed relative to our ideal scenario, it would have been still way better than what we had with this event.
Yeah, the reason why LAT didn't see its own funding was because it was, at the time, Penn was passing over the South Atlantic anomaly, for which they turn off the large area telescope because it's weird. So it was kind of unlucky for me.
Yeah, it was, I think, like a 2-minute, like it was like within 2 minutes or something of that initial turn off. So
Maybe it's a comment that in this case, the small telescope can see it, but I guess also challenges. I mean, now probably these events will be brighter than years expected if they're all like this one. But the sky area is still relatively large because there's so little detection in the small sky area. The challenge then is pointing. More smaller telescopes with robotic, the ability to scan quickly would be robotic and flash images against really. I think it's maybe still necessary, even if now small telescopes can participate.
yeah, I agree. There's of course a big field of view issue. I mean, like at 30 square degrees, if you've got even a quarter square degree, that's a lot of pointing.
Yeah, maybe large field of view telescopes that don't have to go so deep as
There are definitely a class of, yes. There are definitely a class of large field of view telescopes that don't go deep that I think, like what was this, 16th magnitude or something? 18, okay.
Yeah, absolutely.
You'll saturate the CCD, I guess. Anyway, no, I mean, it might be. But then again, we do know that, of course, other events are going to be, we want to get all the events we can, so the ones that are less bright, we want to be able to target as well.
Is there